Good morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today we are discussing about combining spatial enhancement methods. So what are the combining spatial enhancement methods? What we are combining in the digital images. So before going to combining the spatial enhancement methods, we have to abbreviate what is the combining, what we are combining. So the objective is to enhance this image by sharpening it and by bringing out more of the skeletal detail. The narrow dynamic range of the gray levels and high noise content make this image difficult to enhance, but the strategy follow is utilizing the Laplacian to highlight fine details and the guidance to enhance prominent edges. So suppose I'm taking it is one image, I'm combining the two images. Okay, it is a combining spatial enhancement. So it is one example. So what is the goal? To enhance the image by sharpening it and by bringing out more of this one. So it is the input image. So it is the output. What we have the output means sharpening. So the sharpening the input image, that is the enhancement process is going on by bringing out more of the skeletal detail. So it is a final brightness, okay, the contrast and brightness looking to identifying the image. And it is a where image A, image of whole body bone scan, and image B, it is a Laplacian transform. Okay, it is a Laplacian. Next, image C, sharpening the edges of the image by obtaining the original image, and it is a Sobel gradient. It is one technique to find out the original image. Okay, so here there are four images are there. First one is a image of whole body scan. It is an input image, and second one is a Laplacian transform of the original image. That is the input image, and image C is the enhanced image with the sharpening of obtaining the image of original. And fourth one, Sobel gradient, to find out, to identifying the image. Okay, what are the bones are there, what is the structure of there, we have to identify. Okay, so there is a lot of difference from A to B, B to C, and C to D. So it is one example of combining spatial enhancement method. So in this, the objective is to enhance this image by sharpening it and by bringing out more of the skeletal detail. The narrow dynamic range of the gray levels and high noise content make this image. And what is the difficult to enhance? So the strategy will follow to utilizing the Laplacian to highlight in detail and gradient to enhance prominent edges. Okay, it is one thing. And the image shown in the next, the nuclear whole body bone scan used to detect diseases such as bone infection and tumors. So any of the human body, I am taking one input. Okay, what is my output? What is my aim? To body bone scan used to detect disease such as bone infection and tumors. So structure of the body. So how we are finding structure of the body? What is how? The reason is that will be explained that smoothened version of the gradient image will be used to mask the Laplacian image. Okay, from the input image, I am applying the Laplacian for the input image. I am getting the output. So what is the output I am getting? So I am getting the smoothening or sharpening of the image. So what is the technique I am applying? Laplacian transform I am applying to the image. Okay, finally we'll attempt to increase the dynamic range of gray levels by using gray level transformation. Suppose I'm taking, it is the input. For this input, I'm applied Laplacian transform. After that, what is happening? smoothing and sharpening. And what is output means sharpened image or smoothing of the image. So in this image input, I am applying the Laplace transform. So suppose g of x comma y equal to capital T of f of x comma y. Capital T of f of x comma y. So here, what is a transformation function means? I'm applying here Laplacian transform. The input is a g of x comma y is a output and f of x comma y is a input. So what is the output equal to? Transformation function with the combination of the input. That is the output. Here, so here output is a smoothing or sharpened image. So the nuclear whole body bone used to detect diseases such as bone infection and tumors. How can we find out these things in the original image? Means I am applying the Laplacian or gradient function. So what is that means? Smoothened version of the gradient image will be used to mask the Laplacian image. Laplacian transform I am applying Laplacian to the input function. So input image. Finally, we will attempt to increase the dynamic range of the gray levels by using gray level transformation. So it is one example. So it is another example combining spatial enhancement methods. So it is also enhanced image by sharpening it and bringing out by the skeletal. Okay. So what is the difference means? It is the input. It is the output. But what is the means? Contrast. Okay. The contrast is very high. Why? Because why I am increasing the contrast means I want to find out what are the bones are there. I want to maximize. I want to more focus on the bones. Okay. So that is the reason I focused on only bones. Okay. What are the bones are there? That will be highlighted as a white. Remaining all converting it as a black or gray levels. Okay. So here the input is a Sobiel image and the output is a second one is a I'm applied the mask technique or Laplacian form, and third image is a contrast level is somewhat better, but brightness white and black are same balanced, but output final one is what is what means I'm increasing the contrast, I'm sharpened the original image. Okay, so it is a combining of spatial enhancement method, but what is the goal means enhancing the image by sharpening it and by bringing out more of the skeleton. So it is another example of combining the spatial enhancement method. What is the image means f of x comma y. So here I am taking some 3x3 mask. So it is whole input image. For this input image I am applied the mask technique to reducing the noise or smoothing or sharpening. So what is output? G of x comma y. Here output is a g of x comma y. What are the coordinates? X and y are the origins. So image input image f of x comma y, output is a g of x comma y. So g of x comma y equal to mask of f of x comma y. So for the input image I am applying the mask, that is a mask of f of x comma y. In the term of t I am taking. So neighborhood is defined as area bigger than the single pixel, may be of any size or shape. Most used rectangle or around the central pixel might be referred to as filters, kernels, templates or windows. Okay, so the neighborhood is defined as any area bigger than the single pixel, may be of any size or shape. Most used rectangle or around the central pixel might be referred to as filters, kernels, templates or windows. Okay, so it is a mask of 3x3. Okay, the image f of x comma y. What are the origins means x-axis and y-axis are the origins. So I am taking it is a 3x3. What are the coordinates? So what are the coordinates of this one? F of x minus 1 comma y minus 1, f of x minus 1 comma y, f of x minus 1 comma y plus 1, f of x comma y minus 1, f of x comma y, so on. I am taking the 3x3 coordinates. Okay, it is the image and it is a mask size. Why I am taking it is a mask means I am taking here w of minus 1 comma 1, it is 1 comma 1, minus 1 comma 1, 0 comma 0, 1 comma minus 1, minus 1, comma 1, like this. Okay, it is the coordinates of mask. So the result of R is linear filter with the linear filter mask at a point x comma y in the image is capital R equal to W of minus 1 comma minus 1 into f of x minus 1 comma y minus 1 plus W of minus 1 comma 0 f of x minus 1 comma y plus so on W of 0 comma 0 into f of x comma y plus so on. So it is a mask size, mask of 3 by 3. So it is the coordinates W of 1 comma 0. It is the input function f, W of mask size into this one. So mask with multiplication with input. Mask is multiplication with input. Okay, like this. So here I am applying smoothing and sharpening techniques to combining the both images. So how smoothing image is combined? What is the smoothing linear filter? We will discuss. The smoothing linear filter, it is the output response of a smoothing linear spatial filter is simply the average of the pixel contained in the neighborhood of the filter mask. These filters sometimes are called averaging filters or low pass filters. Okay, here I am taking average filter, that is 1 by 9, 3 square. So here I am taking 16, means 1 by 4 square. So it is 3 by 3. But it is the average. I am taking 1 by 3. But here weighted means 1 by 4 I am taking. So these filters sometimes is called averaging filters or low pass filter. Okay. When I am going for the average filter, it is called as a low pass filter. But what is the smoothing filter? It is a linear filter. The output response, it is only using for output response of a smoothing linear spatial filter is simply the average of the pixels containing the neighbor of the filter mask. Okay, so mask is a 3 by 3 and I am taking the size is also 3 by 3. It is an average filter, weighted average. Okay, weighted average I am taking 1 by 4 square, means size is 4. Here 1 by 3 square means the size is 3. Here another example, the original image is a 500 into 500 pixels. Okay, it is the input. It is the input function. So in this input function, it is a mask size n equal to 3. So here mask size equal to n equal to 5. Here mask size equal to n equal to 15. But here it is mask size is 3, 9, 35. Here 3, 5, 15. So you have to see here. Here 3 is there and here 5. Here 9. Here 15. Here 35. So it is showing as a blurring. When the mask size is increasing, n equal to 35, it is showing as a blurring. So another one is a combining spatial enhancement method. The important one is a order statistic filters. So order statistic filters are non-linear spatial filters whose response is based on ordering the pixels. And the median filter for removal of salt and pepper noise. Maximum filter is finding out the brightness points of an image. So minimum filter is used for opposite purpose. So what are the coordinates? I am taking 10, 20, 20, 20, 15, 20, 25, 100 are the values. So these values I'm taking as a sorting the values. Okay, decreasing to increasing 10, 15, 20, 25, 100. So what is a median? Is a 20. What is a maximum filter output? 10. Minimum filter output 100. So how we are calculating? We are using order statistic method filter to find out in the median, maximum output and minimum output. So what is that means? Order statistic filters are non-linear spatial filters whose response is based on ordering the pixels and containing in the image area encompassed by the filter. So the median filter for removal of salt and pepper noise, maximum filter useful for finding the brightness points of an image, and the minimum filter used for opposite purpose. Okay, these are the values and we are finding the median value, minimum value and maximum value. So the X-ray image of the circuit board corrected by salt and pepper noise. So first one is the input image. Here the noise reduction with 3 by 3 averaging mask. Okay, here I am applying 3 by 3 mask to reduce noise or remove noise. So noise reduction with a 3x3 median filter. I am taking the output with a 3x3 median filter. Median filter is also using in low pass filters. Okay. So it is one example of X-ray image circuit board corrected by salt and pepper noise. So in the input image, some corrupted, so some noise is there. So I have to remove. So I have to remove the noises and we have to go as an identifying image. Unidentifying image is converting to the identifying image. How is it is possible means noise reduction with a 3x3 averaging mask. Next, noise reduction with 3x3 median filter. Okay, it is the output function. So input to output, what is that means? It is recognized as a identified image. What is the reason means? I applied here 3x3 mask. First, I'm using average mask. So it is not is in the improve mode. Okay, we have to still improve in the image. Okay, we have to scope to improve the image from the original image. So what is the next process means? I applied median filter. Okay, to improve the images. And the principal objective of sharpening is to highlight fine details of an image or to enhance a detail that has been blurred either in error or as a natural effect of a particular method of image acquisition. So the image blurring could be accomplished in the spatial domain by pixel averaging in a neighborhood. Since averaging is analog to integration, it is logical to conclude that sharpening could be accomplished by spatial differentiation. A basic definition of the first order derivative of one dimension function is f of x is in the function of dou f by dou x equal to f of x plus 1 minus f of x. Okay. So here I am taking sharpening technique. I am applying the sharpening. So sharpening filter. So what is the process? So the objective of sharpening is to highlight fine detail of an image or enhancing the details of the blurred image, either in error or as a natural effect of a particular method of image acquisition. So image blurring could be accomplished in spatial domain by pixel averaging in a neighborhood. Since the averaging is analogous to integration, it is logical to conclude that sharpening could be accomplished by spatial differentiation. A basic definition of the first order derivative of one dimension function is f of x. So what is the equation for the first order filter is that dou f by dou x equal to f of x plus 1 minus f of x. Okay, so it is completely for blurring. So here g of x comma y equal to okay. So here input is f of x comma y, output is g of x comma y, and the function is t. What is the function I'm using here? Smoothing filter. What is the use means? Removing the blurrings. Okay, removing the blurrings. Okay, we have to remove the blurrings with smoothing filter. So g of x comma y equal to the smoothing filter constant value t into f of x comma y. So this smoothing filter is applied to the input. Then we will get the output. So here also the sharpening is a highlight of fine detail of an image to enhance detail that has been blurred either in error as a natural effect of a particular method of image. So the blur could be accomplished in the spatial domain by pixel averaging in a neighborhood. Since the averaging is analog to integration, it is logical to conclude that sharpening could be accomplished by spatial differentiation. A basic definition of the first order derivative is the one-dimensional function. So what is the blurring for the sharpening? What is the function I am using for sharpening means dou f by dou x equal to f of x plus 1 minus f of x. So sharpening filter, spatial filter, what are the applications? It is known as derivative filter. So why I am calling derivative means here I am using derivative. It is a derivative filter. The purpose of the sharpening filter is just the opposite to the smoothing. So what is the advantage of sharpening means it is opposite to the smoothing. Means smoothing is to removing the blurrings, sharpening is to sharp the edges. And the main focus of the removal of blurring and highlight the edges of this. So removal of blurrings, it is first one, and highlight the edges. Okay, so these are the two applications of smoothing. Sharpening, and it is based on the first and second order derivative. First order derivative is for smoothing, second order derivative for sharpening. Okay, first order for smoothing, second order for sharpening. So what is the use of sharpening means? We are focusing about removing the blurrings and highlight the edges. Using sharpening filter, using second order, using second order filter. Okay, so removing the blurring of the input image using sharpening and using second order filter. So the output is a removing the blurring, blurless and sharpened output. So it is a derivative filter, and the purpose of this one is a sharpening spatial filter is just the opposite of the smoothing. The main focus is the removal of blurring and highlight the edges, and it is based on the first and second order derivative. So what is the first order derivative? It must be 0 in flat segments, must be 0 in non-zero at the onset of gray level step, must be 0 and non-zero along ramps. First order derivative is a 1D is given by f dash equal to f of x plus 1 minus f of x. Okay, it is the first order. What is the second order? Must be 0 in flat areas, must be 0 at the onset and the end of a ramp, must be 0 along ramps. Second order derivative is a 1D is given by f double dash equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. It is using for sharpening. So what are the common sharpening filters? Unsharp masking, high boost filtering, gradient, and Laplacian. So when I'm using for the gradient, first order. When I'm going for the Laplacian, second order. Dou f by dou x like this. Okay, I'm using Laplacian of f of x. It is a second order and it is a first order. Okay, what are the common sharpening filters? Are unsharp masking, high boosting, gradient, and Laplacian are the common sharpening filters. So useful for emphasizing fine details. The elements of the mask contain both positive and negative weights. Mask element is sum to be 0. Okay, when applying plus 1 minus 1 equal to the sum of two values are 0. Mask element sum to be 0, or the elements of the mask contain both positive and negative. Positive and negative. Okay, if I am adding both are this one 0. Example, it is emphasizing edges of the image. It is the input image. For the input image, apply mask to input. So it is one example of input image. It is a sharpened output image. So why I am going for the sharpening means better visualization of the original image is typically added to the sharpened image. It is another example. Contrast enhancement has been applied for the better visualization. It is the obtaining the sharp image by subtracting low pass and high pass, and it is adding two images for the sharpening. It is another technique, and it is a high boost filtering example. It is a 1D example, original, blurred. It is a original signal, input signal. It is a blurred signal, unsharp, and sharpening. Okay, it is the output image. So what of the means? Here I am using 1D of the mechanics of unsharp masking, original image with the blurred signal, original as a unsharp masking, sharpened. So final is a sharpened output. So it is one example of 2D. First one is a input image, that is the original. Second one is a Gaussian smooth, G mask, unsharpening, and high boost filtering. Okay, it is a original image, result of the blurred image, and unsharp image, result of the using unsharp, result of using high boost filtering. So what are the foundations of this one? What is the foundation means? Laplacian operator, unsharp masking, and high boost filtering using first order derivative for nonlinear images of sharpening, that is called gradient. So the first order derivative of a one dimensional function is f of x is the difference, and dou f by dou x equal to f of x plus 1 minus f of x1. It is a first order derivative. Okay, it is a second order. So the second order is a f of x equal to dou square f by dou x square equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. Okay, so these are the intensity transaction with a ramp down. When the image is going down, it is a step. Ramp means down, step means up. So the second order isotropic derivative of operator is a Laplacian for the function image f of x comma y, dou square f equal to dou square f by dou x square plus dou square f by dou y square. So dou square f by dou x square equal to f of x plus 1 comma y plus f of x minus 1 comma y minus 2 into f of x comma y. Dou square f by dou y square equal to f of x comma y plus 1 plus f of x comma y minus 1 minus 2 into f of x comma y. Okay. So it is one example of the mask with input filtering. Mask used to implement an extension of this equation, and C and D are the two other implementations of the Laplacian function. Okay, it is a output with Laplacian. So the image sharpening with the Laplacian g of x comma y equal to f of x comma y. Okay, output is equal to input plus transformation function. So here f of x comma y equal to input, g of x comma y is the output sharpened, c equal to dou square f of x y corresponding to that, c equal to 1, either the other two filters is used. Here one sampled image, one example. First one is a input of blurred. Input with blurred. Second one is a Laplacian without scaling, and image C is the scaling function, and image D is the sharpened image using mask. And the final one is a result of using the mask. Okay. Okay, what is the unsharp masking means? Sharpened image consists of subtracting and unsharp smoothing version of the image of the original. Okay, what is that means? Printing and publishing industry. What are the steps for unsharp masking means? Blur the original image, subtracting the blurred image from the original, and add the mask to the original. Okay, what is the function means? G mask of f of x comma y output function equal to input of f of x comma y minus f dash of x comma y. So here g of x comma y equal to output is equal to f of x comma y plus k into g mask of x comma y. It is a k less than or equal to 0. Where k greater than 1, the process is referred to as high boost filtering. Okay, it is one example of high sharpening mask. It is the original signal with input function. It is a blurred signal, unsharp. It is a sharpening filter output. It is one example of unsharp masking. So the function f of x comma y, the gradient function f, and the coordinates are x comma y. So dou f equal to gradient of f equal to gx comma gy equal to dou f by dou x and dou f by dou y. It is the gradient function of the image sharpening based on first order derivative. So the magnitude is equal to dou f. The magnitude vector equal to delta f equal to m of x comma y. So m of x comma y equal to magnitude of delta f equal to square root of gx square plus gy square. So here m of x comma y equal to modulus of gx plus gy. So it is one function of mask. So mask m of x comma y equal to z8 minus z5, z6 minus z5. Here another example, robot cross gradient operation. It is the image sharpening based on first order derivative only. Here m of x comma y is the mask size, z9 minus z5 plus z8 minus z6. It is another function. So it is the Sobel operator function. M of x comma y equal to this one. And it is one example of 3 by 3 region of an image, the intensity values, and robot cross as a B and C as a robot cross section, and D and C are the Sobel operators of the image. It is sharpened spatial image. First one is a optical image of contrast lens, and second one is a Sobel gradient. It is a one method. It is completely black. It is completely in white. So Sobel is converting white to black. So these are the references. So it is about combining of the spatial filters. So it is a combining of spatial filters. What is the objective means sharpening and bringing more of the input image. Okay, and we are prominent to remove blurrings and sharpened images, sharpened the edges. For this one, it is one example of combining of spatial enhancement. Here I am applying the sharpening function. Here I am applying the sharpening. It is another one. So what is output means more brightness compared to the input. Okay. Here I am applying the mask of 3 by 3 size. And it is one example of input function f of x comma y with mask size w of x comma y. And it is a smoothing linear function. In the smoothing linear, two types are there, average filter and weighted average filter. It is some examples of mask size n equal to 3, n equal to 5, n equal to 9, and n equal to 15, n equal to 35. So it is an order statistic filter, and it is an X-ray image, and it is using for removing the blurrings with the sharpening filter. These are the applications of sharpening: first order derivative, second order derivative, common sharpening filters, and it is a mask size with positive and negative dimensions. It is an input and it is a sharpened output. It is a addition of a multiplication of two images for sharpening. It is addition of two images for sharpening. It is one example of removing the blurrings and unsharp the mask. Output is a sharpened. What are the foundation of the sharpening means? Laplacian operator, unsharp masking, and Howe boost filtering. What is the using means? First order derivative and for non-linear images for sharpening and gradient. So the first order filter is the equation, the second order equation, and it is a sharpening image of some ramp and step functions. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.